Okay, welcome to our first lesson for Unit 8. You can see here the objectives for this unit, for this lesson, excuse me. We hope by the time you're done with this lesson, you will understand what an exponential function is, at least one that's of the form y equals b to the x. You'll be able to identify what the base of an exponential function is. You'll understand what an asymptote is, and you'll be able to identify some key features such as the domain, the range, the y-intercept, and the equation of the asymptote. And then finally, we hope you'll be able to explain how the value of the base affects the shape of the graph. So we're going to jump right in and start by considering this function y equals 2 to the x. If you remember, before spring break, we did an activity where we were folding paper in half, and this was the function that we used in that activity to represent the layers of the sheet of paper. To complete the table, it might be easier to start at the bottom of the table first. So 2 to the 4th power is 2 times 2 times 2 times 2, which is 16. And 2 to the 3rd power is 2 times 2 times 2, which is 8. 2 squared is 4, and 2 to the 1st is 2. You may not remember this, but 2 to the 0, in fact, any number to the 0 power is equal to 1. That's one of the exponent properties we reviewed before spring break. Another exponent property that we talked about before the break was negative exponents. 2 to the negative 1 power simply means 1 over 2 to the 1st power, so it's 1/2. And likewise, 2 to the negative 2 power means 1 over 2 squared, which would be 1/4. So now that we've got our table of values, we can plot these points and start to get an idea of what this graph would look like. When x is 4, the y value is 16, which goes off our graph paper, so we can't plot that point. When x is 3, though, we have a y value of 8, so that would be about here. And you can see I'm going to plot all the points that are on the table, or at least I'm going to try. I say I'm going to try because when you start to get to the negative x values, that's where things get interesting. It's hard to plot 1/2 precisely, but I'll do the best that I can. And it's even harder to plot 1/4. But anyway, hopefully I've done a good enough job that you start to get an idea of what this graph is going to look like. We know it goes off the graph paper up here, and it comes down and looks something like that. And we can say that the graph continues to the left, but we'll talk some more about continuing to the left a little bit later on. Okay, so going ahead to the next slide. Like I said, that was a basic example of an exponential function. An exponential function is anything that has the form y equals b to the x. B is what we call the base, and that can be any positive number other than 1. So in the previous example, the base was 2. Now, if you're wondering why we say the base can't be negative or why the base can't be equal to 1, that's worth talking about in a little more detail here. So if we go to the next slide. So here's an exponential function with a negative base. First of all, it certainly is possible to raise negative 2 to the 1st power. Anything to the negative 2, anything to the 1st power is itself. So negative 2 to the 1st power would be negative 2. Negative 2 squared would be negative 2 times negative 2, and that is 4. And anything to the 0 power, we noted this earlier, anything to the 0 power is 1. So even negative 2 to the 0 power is 1. And negative exponents, we explained, simply mean 1 over. That would be 1 over negative 2 to the 1st. So that's 1 over negative 2, which is negative 1/2. Now, first of all, you might notice this is an interesting function because your y values seem to flip-flop from negative 1/2 to positive 1 to negative 2 to positive 4. So that in itself is a bit of a strange function where it kind of goes back and forth between negative and positive values. But that really isn't the problem. The problem is better illustrated when you consider what happens when you have an x value of like 1/2. I hope you remember that raising something to the 1/2 power is essentially the same thing as taking the square root. So your y value here should be the square root of -2. And the square root of -2, I hope you remember, is imaginary, which means it's a number that won't show up on the Cartesian plane. The same thing would be true when you raise to the -1/2, because that would just be 1 over the square root of -2. So that would be 1 over the square root of 2i. And even this x value, 3/2, if you recall rational exponents, that 3 means you're cubing it, and the 2 still means you're taking the square root. So one way to evaluate the y value here, -2 to the 3/2 power means -2 cubed, and then you're taking the square root. Well, -2 cubed would be -8, and the square root of -8, once again, is going to be an imaginary number. So you see, that's the real problem with negative bases, is we would keep getting imaginary values which don't show up on the graph. And so that's why you can't have a function with a negative base. As far as why the base can't equal 1, it's a little bit of a different situation there. 1 to the first power is 1, and so is 1 squared and 1 cubed. And if you play around with this very quickly, you're going to see that the y value is always 1. So this situation, it's not that we can't have a base of 1. It's more a problem of, if you did have a base of 1, what you'd end up with is a graph that just looks like a horizontal line. And that's not an exponential function, that's a linear function. So having a base of 1 is not allowed simply because it doesn't yield a graph that's different from a linear graph. Okay, so moving on. Here's an actual graph of 2 to the x. And if you take a look at it, you'll see that it's got the same points that we plotted earlier, including those fractions. 2 to the -1 is a half, 2 to the -2 is 1/4. If we keep going to the left, again, negative exponents just mean 1 over. So every one of these, I can tell you, is 1 over something. And then the denominator is just going to be, in this case, 2 to the 3rd power, 2 to the 4th power, 2 to the 5th power, and so on and so forth. So you'll notice our y values are getting smaller and smaller and smaller. And if you look at the graph, it almost looks like the graph is touching the x-axis. But if you look at the y values in the table, you can see that, well, it's not really touching, because if it was touching, the y coordinate should be 0. The question is, would you ever get a y value that's equal to 0 or negative? Well, if you imagine this table continuing farther and farther towards the left, so to speak, I hope you can see that no, it's never going to equal 0. A fraction will only equal 0 if you have a 0 in the numerator. So 0 over some number, like 0 over 100 is equal to 0. Your numerator is never going to turn into a 0. Negative exponents always mean 1 over some number. As long as the numerator is 1, you'll never get a y value of 0. You'll also never get a negative y value because the 1 is a positive 1, and the denominator is never going to turn into a negative number. So there's no way you can get a y coordinate that is equal to 0 or less than 0. And that is why this graph demonstrates what we call an asymptote. An asymptote, if you weren't already familiar with this, an asymptote is a line that a graph gets closer and closer to but does not touch. Now you might notice at the bottom of the slide in red, there's a little footnote. That's not technically a correct definition of an asymptote. Later this semester, you're going to see a more precise definition of an asymptote. But for now, it's good enough. And so it suits our purposes. We're just going to leave it at that for now. The x-axis is often the asymptote of an exponential function because, as we explained, you will never get y-coordinates that are less than 0 or equal to 0. I say often, not always, and that's because I hope you know by now that what's coming later is transformations. When we start taking this graph, and let's say we took the graph you see in this slide and imagine we were to shift it down. Well, if we shift it down, then if your graph is down here, well, then you're touching the x-axis right here, and you can't say the x-axis is your asymptote anymore. You have a new asymptote, and it would be down here somewhere. So we'll talk more about that when we're ready to address transformations. So at this point, I'm going to suggest that maybe you get out a graphing calculator, or if you don't have one, go to desmos.com. And why don't you take a few minutes and take a look at each of these graphs. Each of these are exponential functions. You notice that the base is always a positive number, and it's never equal to 1. We'd like you to look at these 4 graphs and take a look at them and think about what do they have in common and how are they different. And after you've had a chance to do that, come back to this and you can proceed to slide 8. So if you had a chance to look at different exponential functions using a graphing calculator or using Desmos, especially if you looked at the 4 that we suggested you consider on slide 7, I hope you noticed that there's a significant difference to the graph when the base is greater than 1 or when the base is less than 1. Keep in mind when we say the base is less than 1, it still has to be greater than 0 because we can't have a negative base. So if you have a graph, if you have an exponential function with a base greater than 1, like 2 to the x, 3 to the x, 4 to the x, it's going to look something like the blue graph you see here on this slide. And the thing that's significant to notice about this graph is notice that on this graph, if you start on the left and you move towards the right, your y values get bigger and bigger and bigger. That is what we call an increasing function. And then we could say that this is true of any exponential function where the base is bigger than 1. It's going to be increasing. But if you have a base less than 1, it's like 1/2 or 1/3 or 2/3, then you're going to get a graph that looks something like the red graph. And again, if you notice, if you start on the left and move to the right, the red graph has y values that get smaller and smaller and smaller, and that is what we would call a decreasing function. So you can see, depending on the value of the base, it makes a pretty significant difference in what the graph looks like. More specifically, it's going to determine if the graph increases or decreases. Once again, though, at the bottom of the slide, we have this unless statement because, again, you know what's coming soon, transformations. Imagine we were to take this blue graph and reflect it over the y-axis. Well, if you take that blue graph and reflect it over the y-axis, then it's going to look something like this. And now, even though the base might be bigger than 1, it's no longer an increasing graph because now when you move from the left to the right, your y values are going down. So we would consider that that red graph that I just drew to be a decreasing graph, even though the base might be bigger than 1. Again, that's a subject for another time when we're ready to talk about transformations. So we're getting close to wrapping things up here. This is a slide that the first part of it is information you saw before. It's the basic definition of an exponential function. I hope you understand what the base is now, and I hope you understand why the base has to be a positive number and cannot be equal to 1. We didn't say this earlier, but you might have noticed it when you were looking at different exponential functions in Desmos or on the graphing calculator. I don't care if your function is 2 to the x, 3 to the x, 1/2 to the x, 1/3 to the x. The domain of any exponential function is always all real numbers. No matter what the base is, it will not change the domain. It's all real numbers. Now the range, that's another story. The range is normally from 0 to infinity. Notice it does not include the 0. Remember, the x-axis is an asymptote. We don't ever touch it. And if we don't ever touch the asymptote, then we're never actually equal to 0. We just get closer and closer to it. The range is normally 0 to infinity, and the y-intercept is normally equal to 1 because any base to the 0 power is equal to 1. The x-axis is normally the asymptote, and these last 3 points, they all say normally because, again, you know what's coming, transformations. If we start playing around with transformations, we can change the range and it won't be 0 to infinity. And we can change the y-intercept and we can change the asymptote. And so all of that will be coming up very shortly. So here's just our list of objectives again, looking over it. I hope you feel that we've addressed everything on this slide. If you think perhaps you missed something, maybe you want to go back and watch it again or go through the slides again. Going forward here, to check your understanding, if you look in It's Learning, you will see an assessment that's titled Features of Exponential Functions. This is an opportunity for you to just check by answering some questions. I think there's 8 or 9 of them. Answer some basic questions to see if you understand some of the stuff we tried to explain here today. And once you feel confident with the basic understanding of exponential functions, you'll be ready to move on to our next lesson, which will be about transformations. Final slide is just a food for thought. And when I say food for thought, this is stuff that you are not going to be required to know. So you can, rest assured that there will be no questions like this on any quiz or test or assignment in the future. But for people who are curious and maybe want to go a little further, here's a couple things that maybe you'd like to consider. And I'd invite you to maybe, start a discussion on the discussion board. If you think you have an answer to these questions, let's see what some of your classmates think, or maybe I will give you a response to, whatever your thoughts are on these. My first question is, so we talked a little bit about what raising 2 to the 1/2 power is, or raising 2 to the 3/2 power. And you saw very early in the slideshow on our table, our very first table of values, we saw that 2 to the 3rd power is 8 and 2 to the 4th power is 16. Well, my question is, what do you think 2 to the pi power is? Pi is a very famous irrational number, and if you remember, irrational means you cannot be represented as a fraction. Now, pi is 3.14 something, something, something. So pi is bigger than 3, but less than 4. So it stands to reason that 2 to the pi is more than 2 to the 3rd power, but it's less than 2 to the 4th power. But how would you know what exactly it is, since you can't express pi as a fraction? So I just let you think about that, and if you're curious or if you want to throw out possible answers, again, maybe start something on the discussion board. Second question is, do exponential functions have a minimum or a maximum? Just to make sure you understand what I mean, let's talk about a different function, not an exponential function. How about y equals x squared? That's a parabola, and it's centered at the origin. And so the lowest point on that parabola is 0. The lowest y coordinate is 0. So we can say that parabolas have a minimum of 0. They don't have a maximum because, as the arrows indicate, the parabola just keeps going up higher and higher. So there is no highest possible value on a parabola, but there is a minimum. The lowest value on a parabola is 0. So my question is, do you think exponential functions have minimums or maximums? And you could consider that just, by considering a particular function like 2 to the x. Or maybe if you think changing the base would affect the answer, maybe you should think about a different function like 3 to the x or 1/2 to the x. Again, if you'd like to, I invite you to post a question or post an answer if you think you have an answer on the discussion board, and we can see what your classmates, or maybe you'll see what I think. Um, anyway, that's it for the first half of this week's lesson. I hope this was okay. And if you've got feedback on this whole screencasting of PowerPoints, I'd appreciate your feedback on that too, because as I said, this is all new to us folks, this distance learning stuff. And I'm, willing to consider other ways of doing things and trying to help you find whatever is going to work best to help you further your education. So good luck, and don't forget to do the assessment on its learning. And when you're ready, we'll see you on the next lesson where we will talk about transformations.